Okay. So for the FMI 05 and 06, those are referring to out of range high and out of range low for current draw. And those are more applicable to outputs than they are to inputs when we're talking about those fault codes for a controller. Okay. So we're going to look at two different ways that we can control outputs on controllers. This is coming from the diagram that we were looking at yesterday. We already had the CAN bus drawn in here. Now we're going to take a look at some inputs and outputs to the controller. So for outputs, we'll start with a simple solenoid here. Okay, solenoid or relay or whatever. This is just a coil of wire, and we're going to ground it. But what that would mean is that inside the controller, we're probably connecting this to, let's say, a 12-volt source. Okay, so we can do one of two things. We could monitor the current flow going through it, and that's completely doable inside of a controller. And when we turn it on, we want to have some current flow, which indicates that that circuit is good. If there was an open in the circuit, you would have an out of range low for current. If there was a short to ground, you'd have an out of range high, and you would likely just set a fault code and not command that circuit on again. Okay. Now there's another way that we can control circuits. Instead of switching on the high side here, because this would probably be to a 12-volt source, right? So what we could do is we could have a 12-volt source going to our solenoid. Okay, our solenoid is going to be connected to our controller. Okay, I'm going to grab my black for ground here. Okay, and the controller is going to switch ground. Now, why switch ground instead of power? And it's at the end of the day, you're turning that same coil of wire on and off, right? Well, why bother switching the ground side instead of the power side? Okay. There's a pretty good reason for this, and one of the things we can do is we can monitor the state of that circuit even if we're not using it, right? That is one of the benefits to switching to ground side. So picture this. If the controller is always looking to see, is there 12 volts over here all the time, wouldn't it then also be able to know if that 12 volts was missing because there was an open in that circuit? Yeah. Okay. And then that would be a good reason to set a fault code indicating that there was an open in that circuit. Right? So if you switch the ground side, you can see if there's power there all the time. If you switch the power side, you don't really have that same naturally built-in way to monitor the state of the circuit until you're actually trying to use it and you're looking to see if there's the right amount of current flow going through it. Okay. Another thing that we do nowadays by monitoring the amount of current flow is if we see that we have too much current flow or not enough current flow going through what we expect to be, let's say, a lighting circuit. Okay, so if I have a burnt out bulb on a lighting circuit, I can very easily set a fault code, or I can just simply shut that circuit off if there's too much current going through it. So by monitoring current flow through output circuits like this, it gives us a lot of options, a lot better options. Okay. Now there's another thing that we can do, and that is we can have sensors that go to a controller. Those sensors, let's see, let's go with a speed sensor, okay? And let's just say that this one here is a 2-wire speed sensor. And this is a variable reluctance, and let's call this one our crank speed, okay? Our crank position. This is an input to that controller, okay? This is a discrete input to that controller. So your crank speed, variable reluctance crank speed sensor, is what we call a discrete. It's not networked. Its signals go straight to the controller, and that's it. We have these discrete outputs. Okay, that means the controller directly controls that coil of wire, that solenoid. Okay, so if that crank speed sensor signal would be useful to more than, say, just the engine controller. Maybe the instrument cluster would like to know that too. Maybe the transmission controller would like to know that. I mean, historically, what we could have done was had multiple crank speed sensors, each sending their own discrete data to each one of those relevant controllers. We don't do that anymore. Now what we do is we take that crank speed data, we generate a CAN bus message, and we just broadcast it on the CAN bus to any relevant controller that needs that information. Okay? That's one of the benefits of networking things together. Sometimes a controller, whether it's an engine controller, maybe a hydraulic system controller, sometimes a controller actually has its own separate sub-network that it communicates with. Okay? So a good example of that for an engine controller would be your after-treatment system. Okay? A lot of your after-treatment system sensors and even the DEF system on it, that's all running on kind of a secondary CAN bus, right? So that secondary CAN bus, let's go ahead and let's add that to this controller that we're kind of fleshing out here. So we'll go ahead and we'll give ourselves 2 extra control units, okay? And if this was an engine controller, you know, one of these, it might be a NOx sensor, one might be, you know, my DEF pump or something like that, okay? Or my DEF module, I guess we should say. And then we would have power and ground going to these modules. So we'll just add this in here. Okay. There we go. Now, what we don't do is we don't send individual commands to these modules. We just connect them via another CAN bus network. This CAN bus network is specific to these modules. So yes, it is a CAN, but no, it's not part of the main CAN bus system for this machine. So you have what could be called the vehicle CAN, and then over here we have this secondary engine CAN, okay? So this right here, this would be a secondary CAN bus. Okay. The purpose of a secondary CAN bus is to give a controller direct and relevant control over things that matter and not go ahead and clog up the rest of the CAN and the rest of the vehicle with unnecessary CAN bus messages. So for instance, the instrument cluster for the most part doesn't really need to know what's going on with the DEF dosing system unless there's a problem, right? And then the DEF dosing system might send a message to the engine controller, which then sends a message to the instrument cluster to notify you that there's an issue. But for the most part, in terms of, you know, monitoring how much NOx is in the exhaust and then dosing accordingly, and then monitoring how much we have after it's gone through the SCR catalyst, we don't need that information on the instrument cluster. It's completely irrelevant. So why clog up the main CAN with all of that messaging? Why not just kind of leave that off to its own separate CAN network? That's why we do this, okay? If you have things like, let's say a hydraulic valve stack, where you have all of those individual little electronic control modules mounted right to each valve spool, all those ones are doing is just running on their own little CAN that runs off of the main hydraulic controller, right? So in a lot of modern equipment, it's very, very normal to have multiple CAN bus networks. And one of the biggest reasons for that is making sure that we don't overload the CAN bus network, the main CAN bus network, okay? There's different CAN bus networks operating at different speeds as well. That's another thing to consider. Historically, I think it was like 250 kilobits per second was the norm, right? That's what we ran at. Nowadays, we're running quite a bit faster speeds on some of these CAN bus networks. That has to do with the fact that there's so much more information being passed back and forth. Okay? That kind of raises the question, what kind of information is being passed back and forth on a CAN bus network? How does that digital communication happen? What are we doing? So I think this diagram here, this is useful to a certain degree, right? It shows us the type of communication that's happening on the CAN bus. Okay. And we even discussed what this might look like if there was a problem with the information that was being passed back and forth on here. Okay. We said that if, for instance, CAN low, let's say CAN low was completely flatlined or missing, that'd be an issue. It's not very likely, though. What's more likely is that CAN low might, or CAN high and CAN low might have this really erratic random pattern on there. That would be very bad messaging happening. Okay. The other thing that could happen is there might be issues with the system where your bus idle time, which is this over here in between messages, isn't a nice, steady, flat 2.5 volts, where it's spiking all over the place. Okay. If your bus idle time is not a nice, steady 2.5 volts, it's entirely possible that we're not dampening out those electrical pulses that we put onto the CAN bus on CAN high and low. And the way that we dampen out those pulses is by putting a resistor in there. That resistor, it acts like a load, and that's what dissipates those voltage pulses that we're putting out on CAN high and CAN low. If we don't get rid of them, they're just going to bounce back and forth inside that CAN line, and it's going to create a lot of noise, which means we're going to have poor communication. Okay. So what's the tool that we would use to be able to look directly at this? An oscilloscope, yeah. Okay. Now, I don't want to spill the beans on all of the diagnostic projects that I have you guys doing in the shop. Okay. But I am going to tell you that an oscilloscope can be an incredibly useful tool for looking at what CAN high and CAN low are doing. Sometimes there's things that you can see with a scope that you wouldn't know just by looking at the voltages with your multimeter. Okay. In terms of what kind of an oscilloscope, if you're curious about getting something like that, like what should you get? There's a couple of different ones. You can go on Amazon, you can get some super cheap handheld ones. You can go to electronic specialty warehouses and spend tens of thousands of dollars on a scope. Those simple little pico scopes that we're using downstairs, those are a good blend between being cost effective and being really good in terms of their capabilities. Okay, so they have a fast enough speed and accuracy that they work well. The software that you use them with, just on your laptop, it is really good software, especially for it being free software. It's really, really good. Okay, but yeah, if you do want to start looking at the output to the CAN bus system on a scope, there's a lot of things you can tell, and we're going to learn about that down in the shop. Okay. Now, as far as what those little blips mean on the CAN, it's irrelevant to any of us. We just know what they should look like when they're good, and we should be able to identify if it's not a good signal. What those messages mean, it's irrelevant. It doesn't really matter. Okay? But what's interesting is the information that's being passed back and forth on that CAN bus. It's just like any other digital information, right? And digital information, it is essentially bits, and a bit is a 1 or a 0, right? And that's, as far as we're concerned, that's how computers talk, right? That's how data is processed. It's just a power signal being on or off, okay? It is something that's either a 1 or a 0. Now, a 1 or a 0 by itself, that basically gives us two options. So what we'll do then is we'll group them together, and in its most basic form, a byte is 8 bits, okay? So that means that a byte, it could be a combination of bits like 111, 0000, okay? So that's a byte of information right there. Now, what exactly that means? Well, again, you can go and take a look at, some binary or hexadecimal type stuff, and you can see, different definitions. What's interesting is you can make 256 different combinations, I believe it is, of those 8 bits there. We don't do that anymore. Nowadays, those little packets, we're grouping them into like 32 or 64 of them. So every time a message is sent, say, inside of this laptop that I'm using here, it's going to be 32 or 64-bit processing inside of there. And that means it's sending 32 or 64 ones and zeros as one packet of information, which gives you a lot more processing power. Okay, we don't care about that. We're just going to keep this simple though. Okay, I can transmit this message, whatever it means, that group of 4 ones and 4 zeros. I can transmit that message two different ways if I want to pass that message from one controller to another. Okay, one way to do it is what we call parallel. Okay, and the other way to do it is via serial communication. So parallel communication means those 8 bits of information, they would all be traveling at once down 8 separate wires, if you want to think of it that way. Okay, so that would mean you'd have to have 8 wires with 1, 2, 3, 4. There we go. So each of those 8 wires is going to simultaneously carry that 1 byte of information from location A to location B. Okay, for serial communication, we have 1 wire, and everything goes in series, one after another, right? So you'd have 1, 2, 3, 4, 1, 2, 3, 4, right? That's what you'd have. When we're talking about different means of communicating, a lot of what we do nowadays happens via serial communications, like USB, for instance, a USB cable, universal serial bus. That basically means we're passing information 1 bit at a time down that wire. Okay? And with USB cable, just your most basic one is going to have probably 4 wires in it. 2 wires are for power, like a power and a ground, and the other 2 are data wires. And with the USB cable, your data wires, they could be broadcasting, they could be receiving, or one could be doing one thing and one could be doing the other. Okay, and that helps to improve the communication speeds. Now, if we go back up here and look at what's happening on our CAN bus, okay, with our CAN bus, what we could be doing is we could be passing messages down the line. And just for example, let's say this was a 1, that was a 0, that was a 0, that's a 1, a 0, a 1, 1, 0, 0, 1, right? I'm just making this up. But the idea of what's happening here is we're sending different bits down that line. And we're sending mirror images of the same information. So on CAN-LO, it means the same thing. Okay? Now, why would we do something like this? Because we have 2 communication wires. Why not take advantage of the increased communication capacity that 2 different wires would offer? Why send mirror images of the same data? And it's all about data integrity. Okay, let's say that you have a CAN bus system and it's handling some pretty important information, like you took your foot off the throttle and you put your foot on the brake and you shifted the transmission into neutral. You don't want the engine revving up and the transmission staying in gear. Those were all communicating via a CAN bus network to do what they were supposed to do, right? Okay. So in order for incorrect messages to be identified and ignored so that stuff like that doesn't happen, we send mirror images of the same data. So if I ended up with data that came back where that bit was missing and it came back as a 0, now I have a mismatch between those 2 packets of information. I'm going to ignore it. I'm going to request that message again. Okay? It has to do with identifying if we have corrupt data or not. That's why we send those mirror images of that same information. Okay? So when it comes to controllers, not only do they need to pass information from controller to controller via CAN bus network, sometimes they need to store information on board so that they know what to do with the information they're handing back and forth, so they know what to do with the outputs they're creating, with the inputs they're receiving. Okay, so that's going to be memory. That's what we're talking about. So we're talking about memory in the context of controllers, or in the context of any computer for that matter. Memory generally falls under 2 categories. Okay, non-volatile. Okay, and volatile memory. Okay, so what's the difference between those 2 things, first of all?
Like a hard set memory, and then so that would be like your injector, like trim files and stuff like that. Volatile, just kind of like you forgot when the tower's completely off.
So yeah, volatile memory. Data is lost. And power is removed.
Short term, long term.
Yeah. So when we're talking about volatile memory, volatile memory is a kind of memory that if you take away the power source, whatever was stored there is just gone. You need power for it to maintain whatever it was trying to store in terms of memory. Non-volatile. There we go. If you remove the power, whatever data was stored there, it's still there. It doesn't go away. Okay. So examples of non-volatile memory that we might be familiar with. Okay, so read-only memory is a good example of that, yeah. So read-only memory is a type of memory that is still technically in use nowadays, but read-only memory is a type of memory where if you write the data to it, it's there, and that's it. You can't rewrite it, you can't erase it, it's just there. Now, I realize my audience, this is 2025, and the number of guys in the room that have probably burnt a CD is probably very few nowadays, okay? But back in my day, burning a CD was something that you could do, or you could, maybe write a movie to a DVD or something if you wanted to. That was a form of read-only memory because you had this data storage device, the disk, and once you wrote the information to it, that was it. You couldn't rewrite it. CD-ROM, that's what they called them, yeah. So CD, DVD, something like that. Nowadays, it's much more common for you guys to, it's not that common anymore, but you would use something like flash memory, which could be like a SD card, USB drive, something like that, right? Flash memory is probably more along the lines of what we would call electronically erasable, programmable read-only memory, or EEPROM. Okay. Now, if you think about it, EEPROM, or the flash memory that's on a controller, okay, that is what we were just talking about. Where if you're gonna, write your trim files and your engine parameters or your transmission shift calibration points, that kind of stuff, that's stored in the EEPROM, or the flash memory part of a controller. Okay. The ROM part of a controller, that would be the part that's not really programmable. That would be the part of a controller where basically it knows it's a controller because that's how it's built and that's what it is. And then when you go ahead and you plug in your service tool to the system that has that controller on it, now you can reprogram certain parts of the controller, but that's the EEPROM that you're writing that data to. But when you're updating your trim files or you're recalibrating your shift points on the transmission, those types of things, it's the memory in the EEPROM that gets programmed. Okay. So if we have a type of memory that doesn't lose the stored data when the power is removed, why would we even bother thinking about using one that does lose stored data when the power is removed? And there's one reason. It's faster. It's way faster in terms of what it's able to do for memory. And the one that we're probably most familiar with is something called random access memory. Okay? It's a very fast type of memory. And nowadays, the amount of RAM that is in a typical cell phone or computer is larger than what a hard drive used to be on a computer, quite a bit larger. Okay. Now, if I think about it, I bet you just my phone right now, I think that thing's got either 12 or 16 gigs of RAM in it. That's more than the whole memory was in the first smartphone I ever had. I think my first smartphone was either 4 or maybe 8 gigs of memory in it. It's crazy to think how far we've come, But the nice thing about having more RAM is it means you have the ability to store more information in that really fast memory. The only problem is if you shut the power off, it's gone, so you have to reload it. Well, that information, guess where it's stored? It's stored over in the non-volatile memory. And we just go ahead and we pull that information into the RAM so that we can use it faster. Okay. On a piece of machinery, again, this is getting to be less and less common, but we do sometimes have a type of memory where if you remove the battery cable, whatever was stored there goes away. You hook your battery cable up, and then, back in 1992, that's how I used to reset fault codes on controllers, right? It doesn't really work that way anymore. But that type of memory would have been called keep alive memory. Okay. The reason I bring that up is because it's relevant in the context of machines that have certain systems where they have to have battery power to those systems in order to maintain whatever data is stored. If you shut the master switch off on a machine, are you truly shutting off every connection to the battery? Probably not. Okay? Probably not. If you want to completely disconnect everything or isolate everything electrically on that machine, you have to pull the battery cables off, not just shut the master switch off in a lot of circumstances. Okay? So you might have some data stored on, again, it's not really that much of a thing nowadays, but it used to be you'd have mapping data stored on your GPS unit, for instance. Okay? You might have some information there that you had recorded and stored that you want to save that site data. Well, you might want to store that on a USB drive before you go ahead and pull power to that GPS. And realistically, nowadays, that's not even a thing. Okay, most of what we have, if it's there, it's already stored for modern GPS units. So we're going to come over here to the lesson, and we'll scroll through some of this here, and let's pause and talk about some things as they come up. So right here, some best practice. It says right here, don't yank the live component, shut the power off, disconnect, and then start unplugging stuff. And if you remember when I was talking about sensor diagnosis, I was telling you guys to purposely short and unplug stuff while it's powered up to try and create fault codes the opposite direction of what the issue was originally. Okay, so there is quite a difference between disconnecting and shorting out a 5 volt 10 milliamp circuit than disconnecting a current carrying 12 volt circuit that could create a spark. You create a spark, that's high voltage, that's how you damage electronics, right? So if you're going to disconnect a main plug on a controller, I would suggest that you turn the power off before you do that. Okay. If you're just going to disconnect a sensor on the side of an engine or a transmission or whatever, yeah, for sure. Unplug it, short it out, do whatever you want. But it goes back to knowing what you're doing. Okay. This last statement here about disconnecting plugs properly. I know how tempting it is to yank on the wires sometimes. But if you've ever been the person who's had to troubleshoot a broken wire inside of the insulation, I mean, sometimes you have a broken wire that you can't see, right? So if the conductor breaks off inside the insulation, it still looks like the wire's okay. And if this is because somebody's been yanking on the wire instead of on the plug, I mean, that just sucks. If you're trying to find a problem like that, like how would you? Okay, so let's say that we do have a circuit, and this circuit has an intermittent fault. Like every once in a while, we set a code. But it's not always there. And it's because of a wire that's broken where you have those conductors touching inside the insulation every once in a while and disconnecting every once in a while. So what you do, in that case, what I would do is I would try to force a code. All right. So let's say it was a sensor circuit. Maybe I'll try and force an out of range high code, okay, by doing whatever, unplugging or jumping some wires, what have you. Force a high code. Okay. And then in your service software, go ahead and pull up that data point. Sometimes you have a graphing option. That's a really nice way to monitor what's happening. So pull up your graphing option and then start wiggling wires. Do a wiggle test. Okay. That's a really good way to find those intermittent faults. If you know what circuit it's happening on, then you can force a known code and start wiggling wires until that code changes state. Okay, or monitor that data. Okay, see when it drops out. I was just talking about the notion of keep alive memory and the fact that shutting off a master switch doesn't necessarily mean that everything is truly disconnected from the battery. So in the context of welding, why does this matter? Well, welding, it's high current, and obviously there's going to be some decent amount of voltage involved there too, as those sparks are busy melting that electrode into whatever it is you're trying to weld. So best practice there, I think you all know this, try to have your workpiece and your ground as close to each other as possible. Isolate the electronics on the machine from whatever it is you're welding. So key off, battery disconnect, batteries actually, disconnected, not just the switch shut off. I have seen some machines where there is warning tags on your controller harnesses that advise you to disconnect those prior to welding. Not every machine, it's not super common, but I have seen some where it says they want those harnesses disconnected before any welding happens. And then we get over here. There was a time where solder and heat shrink, like it was the gold standard for fixing broken wires. Is that still the case nowadays? Some of you guys are shaking your head no. So why would solder and heat shrink not necessarily be the best way to fix a broken wire? It can change the resistance of the wire, and if we're talking about wires that have very low voltage and current going through them anyways, data carrying wires, that can cause data corruption. So we have to be very careful about doing that. Okay, that's one reason. And the other reason is if you have a couple of wires that broke at a certain spot, why did they break in the first place? Probably flexing, vibration, work hardening, and then they broke, right? So if you go ahead and you make a solder connection at that same point where that break happened, you're creating a big hard part in the wire where it wasn't flexible enough in the first place. Okay? And it even gets worse because if you go ahead and strip off the wire, you twist them together, you're going to solder and heat shrink, and then you feed 6 or 8 inches of solder into that connection, and it wicks way up underneath whatever insulation was still there. Now you've got a wider part of that wire, a longer part of that wire that's going to be hard and susceptible to breakage again. Okay? So if solder and heat shrink isn't the gold standard anymore, what is? Scotch locks? No. Believe it or not, actually, some manufacturers are going back to butt connectors. Okay, for whatever reason. Others will recommend just replacing the broken section of wire in the harness. Okay, repinning and putting a new conductor in. That's one way. We don't want to pierce insulation because that's a good way to get corrosion and then, resistances and stuff. And then there's another thing over here where it's talking about wires being twisted. Why do we twist wires? Okay, so let's come back over here and we're going to talk about a notion where if I take two conductors, okay, and I place two current carrying conductors side by side. Try this again. So here's my two conductors, and they're side by side. If one of these conductors has got some pulse width modulated current going through it, that means that wire has a rising and falling magnetic field, doesn't it? And if you have a rising and falling magnetic field, that means those magnetic lines of flux around that wire are also going to interact with any adjacent wires in the harness. Sometimes that doesn't matter. Sometimes it does. Specifically if you have data carrying wires where this may induce a little bit of current in that adjacent conductor. And this we don't want. Okay? So if you have two wires lying parallel to one another, then yes, you can have that interference happening. So instead of that, if I took two wires and I had them running perpendicular to one another, even if I did have this on the blue one here, it's not going to interact with that red one, is it? Okay, it can't because they're running adjacent to one another. So if I take this idea and I take those wires and I twist them, This is why we twist wires. It helps to reduce the likelihood that we're going to have interference from one conductor affecting another. Okay. We can take it a step further as well. I'm sure that you guys have heard of shielding, right? So if you shield a conductor, what exactly are you doing? You're enclosing that conductor with another conductor. That's exactly what you're doing. Shielding is basically just wrapping foil or copper mesh around some wires that you're trying to protect from interference. Okay. So what that shielding does, I'm going to go ahead and I'm going to move this a little bit. Hang tight. Okay. So what that shielding does is even if that twisted pair of wires was in close proximity to some other wires that had the rising and falling magnetic field, the shielding, it might have a little bit of current induced in it. Okay, but what we do is we just go ahead and we dump that off to ground on one side. If you go ahead and you ground your shielding on both ends, you just turn it into another conductor and it doesn't help at all. So shielding gets grounded at one end, and it goes around usually a set of data carrying wires in order to protect them from electromagnetic interference from other wires. Okay. When it comes to your CANBUS system, it's very normal to see twisted pairs of wires. If you have to depin a connector and do any work on it, it's important that you make sure that those data wires, your CANBUS, is twisted back up. We don't want to leave it untwisted because that means it's more susceptible to interference. So if you see a conductor that's got a huge portion of the CAN bus hanging out and it's not twisted, and you're having interference issues and corrupt data issues, that might be something to look at. Okay. Let's jump back over here. Electrostatic discharge, we know that high voltage in the wrong part of a controller can cause some pretty serious and permanent damage. So electrostatic discharge, whether it be a static buildup in your body or on the machine, is something that we should try to dissipate before we start working on electronics. Okay. So I never owned one. I don't know if you guys have one. You know those wristbands that have a little ground strap on them? Does anybody have one of those? Some of you guys actually have them? Okay. If you've got it, and you are doing work around sensitive electronics, probably not a bad idea to use it. But realistically, as long as you touch something metal on the machine and you balance out the electrostatic charge of your body to the machine, you should be okay. All right? It doesn't necessarily fit with electrostatic discharge, but the last statement here about dielectric grease, we use dielectric grease on electrical connections. And do we use it because it's an insulator or because it's a conductor? Okay, it is an insulator. It's not really a conductor. And if we put that grease on our connections, we're not actually really trying to insulate them so much as we're trying to isolate them from moisture and corrosion, right? And the other thing that dielectric grease is really nice for is lubricating those seals. You know those little silicone gaskets on your harness connectors? Sometimes those get pretty dry and they're hard to put together and take apart. The key with this is a little goes a long way. You don't want to put too much in because you can actually end up creating problems instead of preventing problems when you put too much grease into a connector. For terminology, just a quick recap here. CAN, Controller Area Network. When you see ECU or ECM specifically in a test question, it doesn't necessarily mean engine control module. It might just mean electronic control module, so don't read too much into it when you come across that in questions. The bus is the actual physical backbone of that communication network. In the context of a CAN bus, it's the two CAN wires, CAN high and CAN low. All right. A terminator, it's the resistor, it's that 120 ohm resistor. I mentioned yesterday, I don't know if we talked about it in class, but definitely down in the shop, that terminator is sometimes in one of the controllers. Okay, so the terminator might not be a separate component that plugs in at the end of the physical CAN bus harness. It might just be a resistor in a controller, and that performs the function of a terminator. Okay, so be aware of that. If you have a machine and you have two physical terminators on the machine, and you're measuring the resistance and it shows you 40 ohms instead of the 60 that you expect, does that mean that there's a short somewhere in there? Not necessarily. Okay, I have seen and I've heard of instances where we take, say, one manufacturer building a machine and they put a third-party engine in that machine. If they buy an engine that was designed to be a standalone power unit engine, it probably already had a terminator built into its ECM. And then that manufacturer puts their own CAN bus network with two terminators on the machine. So now you effectively have three. Okay, it's something to be aware of. It's not super common, but it can happen. Okay, and then in terms of discrete, we talked about that on our diagram here, where we said we had two examples. We had discrete components. That was these ones over here. Hang on. I love how this corrects me all the time. Okay. So discrete components, those are ones that basically have a single connection to the controller. Networked components, over on the side where we have the secondary CAN bus devices, those ones, they're not discrete because they communicate jointly with other components on the network as well as the main controller that they're hooked up to. So those are not discrete. Okay, so for instance, this NOx sensor here, this is what we could call a smart sensor. Okay.
That's because it's hooked right to the.
Because it's connected to a data network, and that's how it communicates back and forth, right? So if it's a discrete one, it is technically still hooked to a controller, but the wire or wires connected to it, they only have one job, and it's carrying information from that sensor to that controller, and that's it. Okay. So when you're looking at a controller that's connected to a CAN bus network, every controller on that network, it has to have a transceiver. That's what makes it a node on the CAN bus. So a transceiver just basically means it's a transmitter and a receiver. So we can both monitor the data on CAN high and low with that receiver. We can also broadcast onto CAN high or low. You can see that the driver that takes data from the controller, it's going to pull CAN high up to 5 volts. We can see that on top. It's going to pull CAN low down to ground. We can see that on the bottom. And that's what creates that voltage separation from our 2.5 volt carrier voltage when there's data going down the line. Okay. And that gives us the message here. We've seen this picture several times already. Okay, so when CAN high gets pulled up, you can see that yes, we are connecting CAN high to a 5 volt source, but it's on for such a short period of time, it doesn't actually pull it up to 5 volts. It pulls it up. When you're measuring this with your multimeter basically averages out what it's seeing, so it doesn't measure these individual spikes, it just averages them out. And that's why it typically looks like the CAN voltage on CAN high, it can vary. The more communication that's happening, the higher the voltage is going to look on your multimeter. The same for CAN low, the more communication, the lower it's going to look. Okay? Because it's connected to ground more often, basically.